All right. Good day, everyone. Hope you're all doing well, staying healthy. Good morning. Good morning. Today, we're going to finish up the notes for Chapter 5 and 6, go over the last few formulas. These last couple bits have to do with flow. So the how fluids are able to flow. If you recall, fluid can include a liquid or a gas. Both of them are able to flow, and so the things we discussed today are able to apply to both of those things. Sorry about that. So, I recommend you have both the Chapter 5 and Chapter 6 notes, PowerPoint slides ready to go today. We only have about there's only like 2 more slides on the 5 ones, and then we'll go right into the 6 ones, which there's only 8 of them total. So we're going to move through this pretty quickly today. There's just a couple more formulas, all of them very interconnected, very interrelated. Before we get into that, though, I want to go ahead and give you guys a chance to ask any questions that you have, any questions you had while working on any of our assignments, going over any of the material. So, yes.
Problem number 1 of the homework, I'm confused how to figure everything.
Okay, so this is the Chapter 5-6 homework question 1. And this particular question informs us that humans living on Earth's surface are used to a standard atmospheric pressure of 101,325 pascals. This is what you are this is the pressure that your body is always under as long as you're on Earth's surface. What's this? And if you'll recall, the definition of pressure is force over area. So this pressure is caused by air exerting a force on the surface area of your body. Excuse me. And what homework question 1 asks is, basically you're trying to figure out how many sheets of paper laying on your back would be equivalent to this, to give you a sense of scale for how much pressure your body is currently under. So if, say, there was a bunch of paper on your back and you were just laying on the ground feeling how much force that was, the weight of the paper would be exerting a force down into you, and the paper itself has a specific surface area. You recall, the way to find area is just length times width. So each sheet of paper has a specific area, its length times its width. We're assuming that this is a standard 8.5 by 11 sheet of paper. You need to convert those to meters, and that will tell you the area of the paper. And then you want to figure out how much force the paper needs to be exerting for the pressure to equal this. So the first thing you should do is find the area of the paper in meters squared. That'll live here. You want to figure out the force the paper needs to exert a pressure equal to this. So that pressure, 101,325, lives here. Solve for the force. That force is going to be the weight of the paper. Weight is found with mass times 9.8. So you take the force you find here, put it here, divide by 9.8. That'll tell you the total mass of paper. Then it tells you how much.
The inches to meters. How do we convert the inches to meters? Because you said we need to convert the area from inches.
The problem itself does not say, but this would be I'd consider this to be a known conversion. And I don't mean to sound dismissive of this, but I'm okay if a conversion comes up in a homework question, that's an okay thing to just Google.
Okay.
I don't, again, I'm not trying to sound dismissive. I just want to tell you that's where the information is.
Okay.
And so, since we're here, and since everyone's going to have the same numbers, I'll go ahead and let you know 8.5 inches converts to 0.216 meters, and 11 inches is going to convert to 0.279 meters.
Okay.
So, this is just sort of a chain of steps that will take you from pressure to the paper, the amount of paper that will create that pressure. And at the end of it, you will know how many sheets of paper resting on your back would be equivalent to all of the air currently over your head. And there's a lot of air over your head. This is a lot of pressure. So it's kind of amazing what the human body is just handling without you even realizing. Our bodies were built to be able to deal with this. Any other questions about anything at all? Okay. If anyone has any questions at any time, please speak up, put in the chat, cut me off. I want you to be able to ask them. If there's nothing else specific, then I'm going to continue with the PowerPoint notes with you guys. We're going to first conclude the Chapter 5 notes. There's only one more thing on them. And then the Chapter 6 notes are very, very quick. They're just a direct continuation. So, if you open up your Chapter 5 notes and turn your attention to slide 11, we're going to be looking at something called Pascal's principle. Everything we're talking about today has to do with flow. And so this specifically has to do with liquid flowing from one end of a sealed container to the other. And it has this is sort of a before and after situation. If you have a system with flowing fluid in it, so imagine like the pipes in your wall. A system of pipes through your wall. Each pipe has a specific cross-sectional surface area. If you think of the pipe as a can, then the top of it would be a circle, and you can find the area of a circle. So if you were just to take like a thin slice out of this pipe, you'd get a circular ring, and it takes up a certain amount of surface area. And so area represents the cross-sectional surface area of whatever part of the pipe you are presently examining. And well, pipes in a wall can change size partway through the process of flowing through your wall. Sometimes things widen or sometimes things compress, depending on what's needed in a given part of the building. So imagine for a second that you have a pipe shaped kind of like this. It's very narrow on this side, and then it's very wide on this side. What Pascal's principle tells us is, and this is the formula for it, it says that if we sort of look before and after situation, on this side of the pipe, there's a certain cross-sectional, like the pipe has a certain cross-sectional area, and there's a certain amount of force being put into the pipe. Like there's a certain amount of force driving the fluid through the pipe. So we have on this side a 1 and force 1. Now, as the pipe widens, it's going to change its cross-sectional surface area. And according to Pascal's formula, the principle here, the force over the area on the before side will equal the force over the area on the other side. So notice here, we went from a narrow pipe to a wider one. The area increased from before to after. Based on Pascal's principle, what do you think is going to happen to the force of the fluid on this side? If you look at the formula, let's say that each of these things were equal to 1. A force of 1 and an area of 1. This side would equal 1. On the other side, let's say the area increased to 2. Well, the force over the area still needs to equal 1, because we had 1 over 1 on the left. So if the area doubled, that would mean that the force would have to double. So what this tells us is, as the vessel that a fluid is flowing through changes its width, the amount of force it takes to move it, but also the amount of force that the fluid will exert changes. This is the principle which we use in our hydraulic systems. A hydraulic system it's like the sort of thing you might see in a car. It's designed to lift on one side or the other. And basically a piston forces fluid from one end of a pipe of a certain width to a different pipe on the other end with a different width to create a different amount of force on the other side. Now, there's another very specific place that this sees application. And if you move on to slide 12, it'll show an example of that particular place. I want you to turn your memory to any time you've ever been in like a car automotive mechanic shop. In that type of a building, they always, or usually, depending on the fix that needs to be made, need to raise the car up on a platform out of the ground. Because in order to get to the bottom of the vehicle, you have to lift it upwards. So I want you to cast your memory to those shops whenever you've seen the cars lifted upwards. That takes a lot of force to lift a car straight up. So the type of system that they will use to do this is a hydraulic system. Because in a hydraulic system, you're able to get a lot of force out of this side for comparatively little force on this side. What physically happens here is the side with the car on it is basically a giant piston. It's a platform that raises and lowers, and beneath it is a bunch of fluid. We're going to consider this to be a circular pipe, like with our example up here, a circular pipe with a bunch of fluid under it. We call it hydraulics because there's liquid involved. And so as the fluid level rises, it's going to push up on this side of the piston and push up on the car. Now, this side of the piston, the liquid here, is connected to a reservoir, a tank that holds the liquid, and that reservoir is connected to another piston on another side of the building that has a different pipe width, a different cross-sectional surface area, and some other thing is exerting a different force down that side of the liquid. If you remember when we were talking about the states of matter, we consider liquid to have no definite shape, but a definite volume. You cannot compress liquids. So when the force presses down on the liquid here, the liquid it won't get smaller, it won't compress. It is instead going to flow out of this pipe into the reservoir and then up into the other side, and it's going to exert a force upwards. And based on the area of each side of the system, the force that you put into one side will become a different force out of the other side. And the reason we do this is because we'll find in a second, it doesn't take a whole lot of force on the narrow side to lift the car on the big side. So our example with this formula, we're going to prove that fact here and now. So this is our physical setup here. We have a car in an auto shop that has been lifted. We know that the area on the left side, the narrow side, is 25 centimeters squared. The area on the wider side is 2 meters squared. And we're asked how much force it will take on the narrow side to lift the car on the heavy side. Now we're given the car's mass. To lift anything, you have to exert a force equal to its weight. So the force coming up out of this side needs to be equal to the car's weight, which will be equal to its mass times 9.8. So that's going to be, its mass is given to us as 650 kilograms times 9.8. Should give us a required force of, if my memory serves, 6,370. I'm going to check that with my calculator. Oh no, where's my calculator? There it is. Wow. It always ends up on the bottom of the bag, but now it was really hiding. I almost couldn't find it there for a second. Oops. Okay, yes. So on the wide side, we need a force of 6,300 to be what F2 is to lift up the car. So we need to know how much force needs to go into this narrow side to create this force out of the wider side. Now we know the area on both sides, we know the force on the wide side, so if we look at our formula, we should be good to go in order to find the initial force. The one trick here is our first area is given in centimeters squared. It needs to be in meters squared. And because it is centimeters squared, we have to convert from centimeters to meters twice. So this isn't going to be 0.25 meters squared. It's going to be 0.0025 meters squared, because you're going to need to divide by 100 two separate times to cancel out both centimeters and replace them with 2 meters. So our cross-sectional surface area of the narrow end of the pipe is 0.0025 meters squared. Now that everything's in the right units, we can plug things into Pascal's principle. We want F1, and that force is being put into an area of 0.0025. And then on the wide side, we need an output force of 6,370. And that side, the pipe has an area of 2. So now all we have to do is solve for force. So multiply both sides by 0.0025, and that should give us an output force of 7.96, sorry, an input force of 7.96 newtons. This is not a lot of newtons. This is maybe a couple of pounds. So with this system, you can lift a car by only exerting this much force. A human being could come and push into this side of the piston and make the car rise on the other end. So this type of system is very useful. It sort of amplifies the force. Now this doesn't come for free. There is a downside to this type of a system, and it's that if you want this side to raise by a meter, if you want the car to be a meter in the air, you're going to have to push down much more than a meter on this side, because you need to displace the same volume of fluid over here that is being added over here. But you can do that with a lot less force, which does make it easier for a human being to accomplish. Now, in an actual auto shop, we have machines on both sides doing this thing, but this task is still made a lot easier by this type of a system. Any type of a hydraulic system uses this sort of principle, uses Pascal's principle. Any questions on this formula or this type of example? Okay. So, check chat real quick. All right. So, I now recommend you guys pull up the Chapter 6 notes and screen share just so that you make sure you're seeing the right ones. This section is very short. It's just a direct continuation, a couple of things regarding flow. So you should, if you've got the Chapter 6 notes pulled up, the title slide says Chapter 6, Fluid Mechanics. It's a nice shade of skyish blue, that turquoise. It's a nice shade of blue, and the other slides are white with a blue top to them. Slide 2 asks some concept question. Think about these on your own. I'm going to prioritize getting through the formulas in the rest of this slideshow first. But do look at these, do think about the answers. We'll come back to these if we have time, but I want to at least get through the formulas mainly today. So specifically turn your attention to slide 3 for the next formula and the next principle related to flow. And go ahead, get to that slide and look over it as I'm clearing the board. So, the previous equation, Pascal's principle, tells us about how the force on either side of a fluid system, in a before and after sort of a change, how the force changes if the area that the fluid can occupy changes. This next formula, the continuity equation, talks about what happens to the velocity of a fluid in these types of systems as the area of the pipe changes. And according to our formula, instead of force being divided by area, now it's area times velocity on the left equals area times velocity on the right. So let's say that on the left side here, where the pipes are narrow, the fluid is flowing at a specific velocity. For simplicity's sake, let's say the area is 1, and the velocity is 1. So this side equals 1. The left side is 1. On the right side, let's say again that the area doubled to 2. So we have 1 times 1 equals 2 times velocity squared. Sorry, times the second velocity, excuse me. If the area doubled, that means that our velocity needs to be cut in half. Because 2 times 1/2 will be the same as 1 times 1. If the area gets bigger, that means that your velocity is going to get smaller. The reason this happens is because if the pipe is wider, there's more room for the fluid to exist. In this type of a system, the fluid will sort of end up fighting each other to try to get through. If the pipe is narrow and every molecule of the fluid is competing for space, they will try to push through faster. But when the pipe is wider, there's more space. They don't have to try to rush through there. They can take their time. So as the pipe widens, the velocity will get smaller. Conversely, if a pipe narrows, the velocity will rise. And I guarantee you have witnessed this in a couple of different places in your life. We're going to do an example now with this formula that should show you a place where you've witnessed this. So if you move on to slide number 4, we're going to have our first sample question about this particular concept. And on slide 4, it's giving numbers about a specific case with a garden hose. Now, if you can cast your mind to any point in time where you or a family member or someone you know has had a garden hose and was using it to water the grass, wash the car, etc. I already can't talk this morning. I need more water. Now, when using said garden hose, there's a certain cross-sectional surface area for water to exit the hose. And with the amount of pressure driving the water through the hose, with that specific cross-sectional surface area, the water will exit at a specific velocity. But only to cast your mind to a day when someone was using a garden hose like this, but they wanted the water to either come out faster or to shoot farther, why ever they wanted it to happen, you need the water to come out faster. And in order to do that, have you seen them, either if you've done it or seen it happen, put your finger over the edge of the pipe, over the edge of the hose, you just put your finger over it, and suddenly the water comes out faster. All you've done is sort of partially close off the hose, and now the water comes out faster and shoots farther. This exact thing is caused by the continuity equation that we just talked about. And it's because what happens here is when you cover up part of the opening, you have changed the amount of area, the surface area that the water can escape through. You've reduced the cross-sectional surface area. That means the water now has less space. the exit velocity was 1 meter per second. Then, after you have put your finger over the edge of the hose, now the water is coming out at 5 meters per second. Whoops, I don't know why I squared it before. Initially, it was 1 meter per second. Now it's 5 meters per second. What we were asked is, what is the new cross-sectional surface area that the water can escape through? How much of the hose is unblocked by your finger? So we have our continuity equation we can use to solve this. So A1, we have 5 centimeters times 1 meter per second will be equal to A2 times 5 meters per second. We're not set to just do algebra yet, though, because this is in centimeters squared. So we need to, again, convert to meters squared. And again, since this is squared, you have to convert from centimeters to meters twice. So it's not going to be 0.05. It's going to be 0.0005 meters squared. But now we're set to solve for the new area of the exit of the hose. Divide both sides by 5, and you should get 0.0001 meters squared. When you cut the area down to 1/5, you made the velocity go 5 times faster. Now, if for some reason you've never seen this happen with a garden hose, if you've never done this yourself or seen someone cover the end of the hose to make the water come out faster, there are other places that this type of thing happens. A specific example is the shower head. Most shower heads, you can usually rotate something to change the speed of the water. And when you do that, if you've done that yourself, I want you to think back and notice that the water, when you turn it and the water comes out at a different speed, it's not coming out of the same holes at a different speed. It comes out of different holes at a different speed. Most shower heads have numerous openings that are not being used all of the time. And when you adjust the speed, sometimes it just comes out of different holes on the exterior, and you can see that it is coming out of different ones. And if they are narrower openings, on a hose that you can, bend around and be able to specifically aim at your dishes in the sink. And that specific nozzle has smaller holes on it, and so the water comes out faster than just the normal faucet with its wider opening. So this is something you should have encountered before. It's not something that you think about often, but I'm sure a lot of you have probably noticed something like it before. Any questions about this particular principle? Any at all? Okay. There's one more thing that we're going to talk about here, and it looks like a doozy. The remaining formula in this section of notes looks like a doozy. I'm going to show you how to make it easier than it looks. This next formula is going to take everything we just talked about related to flow. Like notice here, both of these formulas involve the pipe changing its area. The next thing we're going to show, the next formula, is going to take all of that and combine it together into a single statement. So this is the last formula for chapter 6. This is the last formula of any total for this week's worth of material. If you move on to slide number 5, you will see Bernoulli's equation. Bernoulli's equation it's a before and after situation. It's a before and after situation. And what it's saying is, before some change in a flow system, before some change happens, on the left side initially, there's a certain amount of pressure making a fluid move at a specific velocity, and there might be a specific amount of fluid above that point contributing to that pressure. But then if some part of that system changes, if any part of that system changes at all, like with our pipe here, how it opens up, if some part of that system changes, then on the other side, there could be a different pressure making things move at a different velocity, and there might be a different amount of fluid above the system causing that thing to happen. This formula, each side of this formula is a mirror of the other one. So, we have 3 terms over here, and we have the same 3 terms over here. Each of the 3 things on each side are the 3 things that can contribute to the amount of pressure in a fluid flowing system. There's external directly applied pressure. This would be like the air pressure around a system. There's pressure caused by the fluid flowing directly. So this term here, fluid density times velocity squared over 2. This term on either side is the pressure added by the fluid flowing. It moves at a particular velocity and causes a specific amount of pressure due to that fact. And pressure can also be added by fluid above that particular point, adding to the situation. Again, remember, this is the same formula that we talked about earlier. Pressure equals fluid density times G times H. This is what we use to find the pressure at a specific depth in a pool. This is what we use to find the air pressure around us based on the height of air above us. This term adds into the system if there's a specific amount of fluid above the point you're looking at. Now, I do know that this looks like a doozy. But we're going to take some time to examine it here today. I'm going to work at least one example with you here today. I know that this is a kind of a big, scary thing to end on. So on Tuesday, we're going to pick right back up here to look at more examples of this. And I'm leaning towards giving you guys till next Thursday to do the homework, quiz, and lab, just so that we can digest this information on Tuesday, and then you can work on things, ask questions on Thursday, and then turn your assignments in Thursday night. So whatever, if we need to cover more of this on Tuesday, that's fine. I'm accounting for that in the schedule. At least for today, I want to do one example of this formula with you before we end. So if you move on to slide number 6, we're going to look at a specific example involving a tub of Gatorade, the type of thing that you'd see at sporting events. So we have a tank of Gatorade. Is it a tank? What's the term for this thing? It is 68 centimeters tall. The fluid level within it is 68 centimeters. It's on Earth's surface, which means that there is constant atmospheric air pressure on all sides of this particular apparatus. And usually the purpose of this sort of a machine is you can come along, you can open the nozzle right here, and Gatorade will flow out of the end and into your cup. Now, if you've ever used one of these things, there's a good chance you've been frustrated by one, because if the tank is full, the Gatorade will flow out at a nice constant velocity and it will make it into the cup and you won't have any complaints. But think about what's happened when the tank was empty. When the tank's empty, barely any Gatorade comes out. And you have to usually like take the machine and tilt it to get more Gatorade to start coming out the other side. The reason for that is, if we consider the before state to be what's happening to the Gatorade when it's right here, so this is our before state, and our after state to be what's happening to the Gatorade as it exits, and we can look at this formula and notice a couple of things. On the initial side, on the before side, there's a certain amount of atmospheric air pressure. The Gatorade isn't flowing yet when it's just resting in the tank. So on the before side of this example, this term is actually 0. If the fluid isn't flowing yet, this term is 0. And there's a specific height of Gatorade above this point, adding pressure down on the Gatorade at the bottom. After you open it and the Gatorade starts flowing, there's still air pressure. The air pressure is actually the same because you're still on Earth's surface. The air level, the pressure of the air hasn't changed at all. So the air pressure is actually going to be the same on both sides. Now the Gatorade is flowing. It is exiting the tank at a particular velocity. And well, once it exits the tank, there's no more Gatorade above it. There's no longer some amount of Gatorade above it here pressing on it. And so afterwards, this term is actually 0. So if we're looking very specifically at this example, the air pressure outside the system is the same on both sides. So this term can cancel out. Initially, the Gatorade's not moving, and there's a non-zero height of Gatorade. Afterwards, the Gatorade is moving, and there is a height of 0 Gatorade. So on both sides, we can cancel out two things when we're looking specifically at this amount of Gatorade. On the before side, the only thing contributing to the pressure on the Gatorade that isn't on the right is just the height of Gatorade. On the right side, the only thing contributing to the pressure of Gatorade that isn't the same as on the left is its velocity. The air pressure is the same on both sides, so it's just going to cancel. Initial velocity is 0, so this goes away. And final height of Gatorade above this point is 0, so that final term goes away, which just leaves us with this statement. The statement saying that the amount of Gatorade above the bottom of the tank is going to increase the pressure and make it come out faster. Like I said before, when the tank is full, the Gatorade comes out fast and you don't have any issues. But when the tank is empty, the Gatorade barely flows and you have to physically jostle the tank to get it to come out of the spout. That's because we know from looking at this particular situation, this particular version of Bernoulli's equation, that the change in pressure from one side to the other is caused from the height, the pressure from the Gatorade above creating the final velocity. So a neat thing about this particular formula is, yes, it's long and a doozy, but usually one or more things on either side are going to just cancel out. So, and actually one more thing will cancel out, because on both sides, density refers to the density of the Gatorade. So we don't even need to know how dense Gatorade is. We can just cancel that out. And now we can just solve for the exit velocity of the Gatorade. So we have 9.8 times 68 centimeters. That's going to be 0.68 centimeters, equal to final velocity squared over 2. We're going to multiply both sides by 2 and then take the square root of both sides. And that should give us a final velocity of 3.65 meters per second. And notice again, if the tank is emptier, if there was, say, 10 centimeters of Gatorade, this H term would be smaller, which means our velocity would be smaller. So this particular formula is sort of it combines everything we've already been talking about into a single statement about how a change in a pressure system can cause a different effect afterwards. This is, again, a before and after situation. And I know we've reached sort of the end of the standard lecture period here, which is why we're going to resume this on Tuesday. I'm going to push the assignments to next Thursday so that you can take what we learned about Tuesday, work on things, and then we can come back and answer questions on Thursday. Tuesday, we're going to talk more about this, work another example for it, and then that'll be everything from this chapter, and we'll move on. To at least give you guys an idea of other places that this sort of thing is useful. This formula is the formula that allows planes to fly. And that's going to be what I show you next time. Our next example is going to be how we can use this formula to make a plane fly. And that's what I'm going to leave you on for right now. If you guys have any questions, please speak up now. If you don't and you have to get to another class, then I hope you all have a wonderful day. If you don't have a class and you want to stick around for any reason to ask any questions you have, you may. But if you don't have any questions and you have somewhere to be, then I do hope you all have a wonderful day and a wonderful weekend. I lost my train of thought as my sentence was ending, but I think that was it. So, yeah, thank you all very much.